Lord, recording is rolling. Welcome to Friday, May 19th. Yeah, so this is last day for seniors. So if you're a senior, yeah, it's been a great year. Really enjoyed teaching this class. Hope you find what you enjoy in life and pursue it and make the most of life. And I hope everything really works out for you. So for all my juniors and sophomores, I guess same message, just yeah, in time. But I'll see you guys for a few more days. All right, so. All right, so I just checked in all the laptops for the seniors that are here. Just got one absent, but here, I'll deal with that later. All right, so let's pick up where we left off yesterday with semester 2 posters. Again, trying to teach you guys as much as I can, and we just got last few days here. All right, so okay, so we were looking at optics. We were looking at waves yesterday, and then optics, and then we're looking at telescopes. And this reflecting telescope, which is a type that Isaac Newton invented, is the foundation for all modern day telescopes. I found a few images that are captured with telescopes. Now, this one is actually not from the visible light spectrum, although it's been, I guess, translated to visible light, right? But this is as far back in time as we can see, right? As far back in time. This is like when light first emerged in the universe at 380,000 years after the Big Bang, right? This is as far away as we can see. This is the edge of the observable universe. Now, the universe almost certainly goes on beyond this. It might be infinitely big, which is crazy for a number of reasons, but that's as far back as we can see. This is the Hubble Deep Field, so it's captured by Hubble. This is where the bell rang yesterday. What I'm trying to show you guys here is what's called an Einstein ring. Now, that galaxy that you're looking at that looks like a ring is not actually ring-shaped. What it actually is here, if I flip my screen over here, well, here. I guess if you're watching a video, I'll just show thumbnail size. Right. Well, here's a refracting lens. This is a magnifying glass, of course. Right. You guys see it makes the image all like wonky, right? Refracts the image. Now, there's a similar effect with gravitational lensing. Now, you might say, well, hold on. In Newtonian mechanics, doesn't gravity only affect attract things that have mass? And I thought light has no mass, so how can light be affected by gravitational pull? But if you get into relativity, what gravity is from an Einstein point of view is actually a warping of space-time fabric. So light always travels in straight lines, but it's traveling on a curved space-time, right? And so there's something called dark matter. There's a mystery as to what it is. It's dark to our knowledge, it's dark to our vision, but there's some kind of gravitational effect that's causing this. It's causing that gravitational lensing effect. Come back to that later. Black hole. You guys may have seen this. This was released, I think, in the last year or two. So this is a picture of a black hole. It's not a single snapshot like you just grab with your phone. This is taken over a long period of time. I think with multiple telescopes too. So anyway, so there's some fun ones. All right, moving on. New stuff. Electricity. Now, I did take a couple of days to tell you guys about electricity, electric circuits. Hold on. Let me pause this. What's going on here? Okay, recordings resume. Yeah, so sorry about that delay. There's all kind of crazy testing stuff still going on, but yeah, try to make the most of this. All right, so I did take a couple of days to tell you guys some stuff about electricity. That was way too fast, so I'll go over again. Maybe sometimes if you haven't figured out this trick yet, sometimes if you see something once or twice, and it's like your brain just doesn't really have time to process it, which honestly is the case, right? But then you might see it several days later, just because your brain has been exposed to it. Suddenly it like clicks. Right, so that's what I'm kind of hoping is going to happen here. All right, so here are some electricity variables. You got a point charge measured in coulombs. Example is like you rub a balloon against your hair, it charges it up. Right, you can like stick it to the wall. Right, there's an attraction there. Right. Now, if you can get that charge to flow at some rate, that's called electric current. Now, the symbol for that is I as a variable, and the unit is amps, capital A. Right. Remember, there's like a unit. Okay, there's a variable in a unit, just like what was this, right? Okay. Next one, electric potential, also called voltage, right? For like a voltage difference. Guys, when you pop in a AA battery to an appliance, that AA battery has a number of volts. Does anybody know how many volts is a AA battery? 1.5. If you put two like stacked on one top of each other, that makes 3 volts. You guys know those little tiny boxy batteries that are like 9 volts? And in your car, you probably have a battery that's 12 volts. So there's a battery that's like trying to push electricity through, right? And that's supplying some amount of voltage. Now, this is the only one where I might use V as the variable and also V as the as both the variable and the unit, right? Sometimes you see this epsilon or sometimes delta V for electric potential, like a difference in voltage, which is really right? What drives that, right? Think of it as kind of like pressure, like you put in a battery's kind of like a pump, right? Resistance, a classic example of a resistor could be a light bulb. There's something that's resisting the electricity. Now, if you don't have a resistance, that's actually bad. Like, has anybody ever taken a paper clip and attached the negative to the positive end of a battery? It makes the paper clip really hot, really fast. It might burn you, and it drains the battery really fast. That's because that paper clip has almost no resistance, right? Which is not an ideal situation. That's actually called a short circuit. You want to really avoid that scenario. If you drop your phone in water, probably ruins your phone because it shorts it out. Because now that water has electrolytes in it, and it will create pass-through electricity that's not routed where it's supposed to go. It shorts it out. All right, finally, power. You guys know from last semester, power is a rate of energy. That's like joules per second. That's called watts. But there's also an electricity tie-in. Right. Here's an extended list right here. So further, I break down those units. Guys, look up here. Try and help you out. Right. And then I threw in some other ones here. Capacitance, inductance, get into a little bit. And then magnetic field, measured in Tesla, you can measure magnetic field strength. That's going to come out in with inductance. Like, how is electricity generated? And for that matter, if you have electricity, how do you make things move? Like have a ceiling fan turn or a motor, right? You need some kind of electricity. Electricity plus magnetism. Okay, so start with the basics here. Coulomb's law. Suppose you have 2-point charges. Here I have a positive and negative. You guys know opposites are going to attract. If I made them the same sign, like positive, they would repel. Now, what's the magnitude of that force? Okay, so I just talked about the direction of the force, but what about the magnitude of the force? Right, it looks a lot like universal gravitation, doesn't it? Like G_m_m over r squared, right? But now it's K_q over d squared. So there's still a constant. Now it's electrostatic constant, which is now a huge number. Remember, gravity constant was like 10 to the negative 11. This is like 10 to the 9. That's like 20 orders of magnitude different, right? This is much stronger force than gravity, much stronger. We got each Q represents the point charge you can measure in coulombs. D is the distance. There's still an inverse square relationship between the force and the distance, just like there was for universal gravitation back in Newtonian mechanics. All right. So voltage, resistance, and current. When I first learned this back in high school, it took me a few weeks to understand this, but it finally clicked when I was taught this analogy right here. Voltage, think of it like pressure. When you pop a battery into an appliance, think of it like a pump, like that battery is trying to pump electricity through. Right now, how much electricity actually flows through? I could call it the current measured in amps. Think of that like the flow rate, like gallons per minute or cubic meters per second, like how fast is water flowing through? And the resistance, think of it like the reciprocal of the area, like if there's a crimp in the pipe, right? Which ideally is something that you would want. Okay. Right. And what connects those three variables that I just showed on the last slide is something called Ohm's law. Super important, super fundamental in electricity physics. Ohm's law. So the current that flows is directly proportional to the voltage. So like if you double the voltage, you'll double the current. Right? Also inversely proportional to the resistance. So if you put in more resistance, you get less current flow. Right? You guys see that? Okay. So we got Ohm's law. Right. All right, let's step ahead to Joule's law, which brings in power measured in watts. Notice Ohm's law says nothing about power in watts, right? But you might pop in a light bulb that says like 40 watts. Okay, well, where's that on here? Well, it's not really, right? There's some filament maybe in the bulb that would correspond to that on some particular electric grid, but okay. All right, so P is power measured in watts, right? Now here's 3 different perspectives. It could be current times voltage. If you know how much current, how much voltage, I should say like a voltage drop, right? That could get for you. And then actually, if you start from any one of these boxes and you substitute in Ohm's law, you can get the other 2, right? So these are all consistent with Ohm's law, just with the substitution, okay? Right, current squared times resistance or voltage squared divided by resistance. Depending on what problem you're given, sometimes any one of these can be the most convenient version of Joule's law to use. Here's an analogy, so bring back to analogy. So remember I told you that current is kind of like a flow rate and voltage is kind of like a pressure? Hey, your battery is kind of like a pump, and suppose this light bulb is like maybe like pulling energy off that system, off that circuit, right, turning into light and heat. That's sort of analogous to maybe like if there's water flowing through this pipe that's like making this water bill turn, right? It's pumped up to some pressure, there's some flow rate. In fact, the units work out exactly. If you do flow rate times pressure, cubic meters per second times pascals, that gives you watts. Guess what? Current in amps times voltage in volts gives you watts. Okay, so it's actually a really solid analogy. Okay. Flashlight schematic. So if you see 2 parallel lines, one shorter than the other, that means battery. In fact, the long lead is the positive, the short's the negative. Okay, right. An example of a resistor could be a light bulb. This right here is a switch. Boom. That could be a flashlight. That's a flashlight. You guys get that? Good. Right. Let's look at resistivity in a wire. Right. What determines how much resistance is in a wire? What if you made a resistor? Right. Well, the longer the wire, the more resistance. That's directly proportional. If it's 3 times as long, 3 times the resistance. Right. The fatter the wire, like the more cross-sectional area, it's actually less resistance. It's easier to push electricity through. That probably makes sense too, right? A thin wire has more resistance than a thick wire, right? And one more thing is resistivity. What about like a copper wire versus an aluminum wire? Well, that's a material property. That's what this blue one is, resistivity. Greek letter rho, we've used in the past for other things, okay? If you come across this someday, a lab that I really like to do that I skipped with you guys is, do you guys know that Play-Doh actually conducts electricity? Did I tell you guys that? Play-Doh, right? You can make a Play-Doh cylinder, and then you can like hook up like an LED here, and you can actually run electricity through it and show that electricity like has to flow through the Play-Doh cylinder. Okay? And you can actually do this lab where you can change the length of the cylinder, the cross-sectional area. You can measure resistance with a multimeter and Ohm's law, and you can calculate what is the resistivity of Play-Doh. And it's approximately 0.25 ohm meters is what it comes out to. It's actually a really good lab. So I don't know, if you teach physics one day, then there's a good lab to do. Right. Resistors and circuits, this is what they look like. Right? I know it's a cartoon version, but you can read these bands, and these colored bands tell you what the resistance is. So in this case, the first two bands will tell me the first two digits. You got two sig figs, right? So brown, green, that looks like 1, 5. Okay, so I got a 1, 5. Then I got a red band. Now the third band tells you an order of magnitude. So red means 2, but in this context, it's 10 to the power 2. So that's like 1,500 ohms. Okay, great, 1,500 ohms. But there's a plus or minus factor. So one last thing, the tolerance. This gold band tells you plus or minus 5%. Okay, there you go. There's how you read resistors. Right, so resistors in series, if they're one after another, if you hook them up one after another, that will increase the resistance. You just very simply add them. So if it's like 1 ohm, 2 ohm, 3 ohm, you say 1 plus 2 plus 3, that makes 6 ohms. So that would be 6 ohms of resistance. Boom, just add them. Okay. Now, if they're wired what's called in parallel, see, it's like rungs of a ladder. You guys see how here in the previous slide, whatever current is going through the circuit has to go through every single one sequentially. 1, 2, 3, right? If you're driving around town, you have to hit this set of red lights, and then this set of red lights, and then this set of red lights. You have to hit them all before you get back to the parking garage, right? And it has to be a complete closed loop for the electricity to flow, right? You can't have an open circuit like this flashlight. Electricity won't flow if it's open. It has to be closed, right? For it to flow, right? But what about here? Do you guys see how, like, if you're driving around town, the current has to split, and current is sort of analogous to traffic flow. So part of the traffic cuts this way, part of it cuts this way, part of it cuts this way before it drives back around back to this parking garage, which is like the battery. Okay. So you don't go through all the red lights. You kind of choose, and the traffic splits. Well, what if there's like 3 red lights here and 2 red lights here and 1 red light here? Do you think most of the traffic's going to go through 1 red light, and then a little bit's going to trickle through like the others, right? Maybe a tiny bit traffic goes through 3 red lights, right? So the current's going to split. Okay, now I'm getting ahead of myself. From the point of view of the battery, though, what is the total equivalent resistance? And there's 2 ways to sort of get it. One way is you can use this fraction method. I'm cutting past the proof that would prove this, but if you add the reciprocals of resistance and then you take the reciprocal of that tells you the total resistance, right? Now, if you only deal with 2 at a time, there's actually a kind of a faster method that's more go-to, which is you can do product over sum, but that only works for 2 at a time. Now, you can still use this for 3, but you have to chunk it into smaller parts. So I might do A and B, product over some of those 2, write that number down, pretend that that's one effective resistor, and then bring in C and do product over sum with that. And then I could get resistance for the entire circuit, right? Now, there's an analogous story that I always use for this because the math works out the same. By the way, all the stuff I'm telling you with electricity and circuits also applies to other scenarios. Like, for example, I've been telling you guys the analogy of like water flowing through pipes. If you are a pipes engineer one day, you're designing a pipe system and you're watching water flow, you can use the same math. If you're a traffic engineer one day and you're designing roads and traffic flow, you can use the same math, right? Red lights are kind of like resistors. The cars that flow is kind of like current in amps. If you are putting together any large project and you have like teams of people working, it's like, okay, well, we have to do some steps in series, like sequentially, like this has to happen before any of this can happen. And some steps in parallel. Like once that happened, okay, no, well, now we can do these 3 steps all together. And we get this team working here, this team working here, this team working here. Again, all the same math emerges. And here's the next analogy that really brings into that. What if you have like 3 guys painting a fence, and it takes this guy like 9 hours by himself? It would take him 9 hours to paint. Actually, let me change the number. Scratch that. Start over. Okay. Let's say it takes you 3 hours to paint a fence. Like, oh man, I got to do this whole job by myself. It would take me 3 hours. All right. But then you team up with a couple of other people. It takes this guy also 3 hours by himself, and this guy also 3 hours by himself. If you have a 3-man team, and individually it would take them each 3 hours, but now they're a 3-man team. How much time is it going to take them to paint that fence? 1 hour, right? Because the time actually goes down because they're working in parallel. Hey, let's try this out. Guys, what is 1/3 plus 1/3 plus 1/3? That's 1. Now, there's still one more step. Take the reciprocal. What's 1 divided by that? 1/1 is still 1. Hey, do you guys see how the math is the same? Right? Again, you could do product over sum if it's just working 2 at a time. But okay, right? You guys see that? If you're working in parallel, either circuits or like people working in a team, you can use this math that you're looking at this slide right here. Okay, right? All right, Kirchhoff's rules. This looks a little intimidating, but until you jump into this, then actually this starts to make sense. Right now, Kirchhoff's rules. There's really only technically 2 rules if you learn this. Right? There's what's called the loop rule, and the junction rule. Right? So let's start with the loop rule. If you identify any loop in a circuit, the voltage has to sum to 0. So, for example, let's say this battery pumps up 9 volts, and then it drops 3 volts here and 6 volts here. Right? So up 9, down 3, down 6. Doesn't that sum to 0? Right? Up 9 and then down 3, down 6. Right? Okay. What about like down here in this parallel type setup? Well, what if it's like up 9 volts here? Now here I can tell you it has to be not down 9 volts here and down 9 volts here, even if these are different resistors. So this would be up 9, down 9, up 9, down 9. Or what if you went around the outside track? Up 9 volts at the battery and then down 9 here. Up 9, down 9. That still sums to 0. Right? The sum of the voltages in the loop has to go to 0. Right? Or here's a tricky one. What about this loop right here? This is also a loop. Now here's going against the current and then with the current. So it still sums to 0. The voltage drops. Okay. All right, so that's the loop rule. The other rule is called the junction rule. Now this applies if the current ever splits, which it doesn't in the series setup I'm showing, but it does in the parallel setup. See how like the current could be coming around like so many amps and then it splits right here. It splits part that way, part that way. Right? Like the traffic flow has to split, right? But it has to all add up. So if you have like let's say you have 9 amps coming through, 9 amps. Maybe it could split like 6 amps go this way and 3 amps go this way, but it has to add up. That's the junction rule. Okay. Now there are some other rules that sort of fall out of this, and I went ahead and just list them all out here. That's what the and friends is all about. It's all these other boxes. All right. So let's go back to near the top here. For a series setup, the current has to be the same everywhere. Again, if these are different resistors, it's still the same traffic flow that go through these red lights and these red lights. Right? Same number of amps go through all of them. Okay. Now the voltage drop is going to be proportional to each resistor. So let's say this is like 1 ohm and this is 2 ohms. That means the voltage is going to drop a proportion of 1 to 2, right? So if you got 9 volts, it might drop like 3 volts and then the other 6 volts here. That's a 1 to 2 proportion. That's exactly what this says here. The voltage drop is proportional to that resistor. Okay. All right. Everybody got that? All right. Now let's move on to the parallel setup. The parallel setup says, for this particular setup I'm showing you here, the voltage drop has to be the same across each of these resistors A and B, even if they're different resistances. If resistor A is like 1 ohm and resistor B is like 100 ohms, it doesn't matter. They both drop the same number of volts. In this case, it would match the battery. Battery might be like 9 volts, for example. Okay. All right. Okay. We covered the junction rule. All right. Now this very last rule. And now this one takes a little more thinking, but it makes sense if you think about it. So this one says that the current that goes through branch A is actually proportional to resistor B. And I want you guys to see why that would make sense. Let's say resistor A is like 1 ohm and resistor B is 2 ohms. You guys got that? 1 ohm versus 2 ohms. Hey, that's kind of like 1 red light versus 2 red lights. Guys, if you're driving around town, you got to get back to this parking garage, which is the battery, right? And you look down this street and you see 1 red light. You look down this street and you see 2 red lights. Which street are you going to take most of the time? I'm thinking 1 red light. Do you think most of the traffic's going to split through 1 red light? Yeah, that's going to happen until, of course, the traffic starts to build up. And now the other road is starting to look a little bit appealing. Now maybe some of the traffic's going to go that way. Okay? In fact, the traffic that goes through resistor B is proportional to resistor A and vice versa. So if this is 1 ohm and this is 2 ohms, I can say that 2/3 of the current is going to go through the 1 ohm guy and 1/3 of the current goes through the 2 ohm guy. That's exactly what this says here. Okay, that's it. Okay, so there you go. There's how to split it. Waterfall analogy. Here, I'll go ahead and tell you guys this. I don't know if it would or not, but I haven't really seen this in any American textbooks. I saw this in a Japanese textbook once. I thought, oh, actually, this makes a lot of sense. This is really cool. So, and I think this really clicks. It maybe makes this right. So here, suppose you're like pumping up like 9 volts here. Maybe this could drop like 3 volts, 3 volts, and 3 volts. Right? You guys see? Now this is all a series setup. You guys see that's all series right there. Okay. And see how the current has to be same everywhere. This is a visual that backs up these rules right here. And actually, it's specifically for like this top one. Right? Is that right? What if it's all Oh, okay. And then I came with a Kirchhoff table. So I had my other classes do these. So what if I give you the numbers that are in gold? See how there are 4 boxes that are shaded gold, right? That could be like given values. So in this case, I gave you the battery was 12 volts. So I got a 12-volt battery. Great. And I gave you each of the resistors, 1, 2, 3 ohms. You can calculate the equivalent resistance for the entire circuit. In this case, you just add them up because they're all in series. You can calculate the voltage drops, which again are proportional to each resistor. See that? Say 2 to 1, 4 to 2, 3, 6 to 3. They're all the same proportion, right? And the voltage drops add up to 12. There's the loop rule right there. Current, you can use Ohm's law. That's V over R. Voltage drop on resistance. 2 over 1 is 2. That's amps, right? And so on all the way down, right? But look, it's the same current everywhere, right? You guys see that? Because again, it's a straight series setup. And finally, power in watts, you can use Joule's law. And I gave you guys 3 different versions of Joule's law. One was current times voltage. 2 amps times 2 volts is 4 watts, right? And now you got the power output for each individual resistor. And then they all add up to the power supplied by the battery. Okay, is that right? Here's one for a parallel setup, right? So what it look. Oh, and look, there's a visual that tells you the voltage drop has to match the battery for the straight parallel setup, right? And then boom, there you go there. Kirchhoff table, same logic, but kind of glossing over this, right? It's all being video though, if you want to go back and look at this a little bit more. Okay. And what if you have something a little bit more complicated? This is not a straight series or a straight parallel, but it has kind of components of both, right? All right, so here you can navigate those Kirchhoff rules and friends a little bit more and come up with a table that looks more like this. Okay, this one takes a little bit more thinking, right? Maybe it's kind of like a complicated puzzle, but there you go. If anybody's doing electrical engineering one day, though, this could be like pretty fundamental exercise to something that you'd have to know, right? Right, circuit. Here's some things you can put on a circuit. Voltage source. Actually, this is specifically a symbol for a battery, which is a type of voltage source. Here's your resistor. I talked about those. Right, now, what about the ones I haven't talked about? The curly looking guy is called an inductor. That will cause current to lag. The 2 parallel lines called a capacitor. Ben Franklin worked with those in the day. They called them, what do they call them? Leyden jars, I think. That will cause the voltage to lag. And this S-looking shape is called a fuse. You want to wire that in series. And if there's too much current that flows, say like you plug in an appliance and you accidentally like shock yourself or something goes bad with electricity, what it'll do is it'll break that fuse and it'll cause the current to cut off, which is good for safety, right? Okay, that's not everything you can put on a circuit, but that's a lot of the classic things you can put on a circuit. Right, multimeter. If you ever break out a multimeter, a lot of the modern ones are digital. They actually have different functions in them. You can switch a toggle switch, say, do I want to measure basically volts or amps is the 2 main things you measure. Now, and you measure them in different ways, okay? Now, the voltage, you're actually measuring a potential difference. So you want to wire it in parallel with the resistor. So there's going to be like a voltage drop across this resistor, or actually across the battery too. I could put it in parallel across the battery. If this is a 9-volt battery, it should read pretty close to 9 volts, right? Because you're measuring a potential difference. It's like you're measuring the height of a waterfall. But current is a different story. You want to force the current to flow through the multimeter, like through the ammeter. So you have to connect it in series. See how you break open the circuit, force the current to flow through, right? And that will tell you how many amps flow. Okay, so different ways to wire up a multimeter to measure these different aspects. Here's a breadboard, what it looks like on the front, what it looks like on the back. The term comes from when people were first wiring up the very first electric circuits, probably still like 200 years ago. They would physically take a breadboard from the kitchen and start like soldering like holes and put things together, right? And they realized, you know what, this is such a useful piece of equipment. Let's just like standardize this thing. And they came up with this. So on top, it looks like this. You can plug in different little LEDs. You can plug in wires. You can plug in batteries. Plug in. I've seen people make complicated circuits and turn this into little tiny robots that they can like go around a table. And this is like the base of the robot, right? Put little wheels on it, right? What does it look like on the back? This will tell you how you can wire things together. So like these 5 dots are connected. These 5 holes are connected, right? These 5 holes are connected, and so on all the way down. So that tells you, well, you wouldn't want to put an LED here and here because it would just short out and it would never turn on. But if you wired an LED across this bridge right here, they're connected like here to here. Right now, it's something that could actually complete a circuit. There are what are called rails or buses that run along the entire length, right? So these are all connected here. Okay, so there you go. There's a breadboard you can use to wire circuits. All right, let's look at different components. Battery. You have a cathode and an anode separated by an electrolyte. This is not the only type of battery you can make, but this is one. There's a potential difference here of about 1.5 volts. Right, so there's a classic battery. Right. Here's a capacitor. Literally 2 parallel plates could store energy temporarily in an electric field, and it causes voltage to lag. Right. Here's an inductor. It will store energy temporarily in actually in a magnetic field, right? Whenever you run a wire, actually, whenever you run any electricity through a wire, it always generates a magnetic field around it. But if you then wrap that wire in a circle like this, that creates an inductor. It actually linearizes that magnetic field and creates an electromagnet. This you could actually just call it an electromagnet as long as it has electricity running through it, and it causes the current to lag. So these two components, capacitors and inductors, if you have, let's say you have an old TV set and you unplug the TV set, and you're like, hey, I want to like open this up with a screwdriver and dig around in it and kind of explore and see like how is this put together? Good idea or bad idea? It's unplugged. Can it shock you? Yes, it can shock you because these capacitors, also inductors to an extent, but especially capacitors, can effectively sort of act like batteries. And so they can store energy in these electric fields, and you can still get shocked even if the appliance is not plugged in. Actually, I think I have a Faraday flashlight here that has no battery, but I got it right here. Right. So here, switch over. Right. Actually, I'm gonna kind of give away some of my next slides here. Here, I've got a huge magnet here. I got a coil of wires, which is effectively an inductor. Shake this back and forth, and there's a capacitor here. No plastic battery. There's no battery here. But what I'm doing is I'm generating electricity by forcing this magnet past this wire, and then boom, got light right here. Okay, it's a Faraday flashlight. All right, back over here. All right, right-hand rule for electricity. So we got force measured in newtons, current measured in amps, length could be measured in meters. B's magnetic field, you can measure that in Tesla. If you have any two of these three variables lying around perpendicular to each other, you can get the third one pop up. Now, this might remind you sort of torque. There was a right-hand rule for torque. There's also a right-hand rule for electricity, right? This is the basis behind generators and motors, right? So here, these slides kind of go together. If you force a wire through an inductor like this, it will generate a voltage. Epsilon is also used for voltage, right? N is the number of coils. The more coils you have, the more voltage, right? And then the rate change of flux. Flux is this magnetic field times this area. Right, so here, let's put it all together. If you have a waterfall, which is mechanical energy, rotates this water wheel, forces this coil of wires to turn past this magnetic field, that will generate electricity, puts the energy onto the electric grid. Then somewhere, let's say in your home on the other side, now you have a current running through this wire, run that past the magnet, that will generate a force according to that right-hand rule, which converts that electric energy back to mechanical energy. Now you can like turn a ceiling fan, run a motor, okay? So we got two devices here, a generator and a motor, okay? But you see they're just mirror images of each other. Inductive coupling, here's how you can step up and step down voltages. This one thing that gives alternating current an advantage over direct current for electric grids. You transmit electricity more efficiently this way. Okay, anyway, you guys look at it. Inductive coupling, you transform. Do you guys notice the red wire and the green wire are not touching? So there's also a wireless transfer of electricity here, wireless transfer. Anytime you have wireless transfer, it's probably something like this going on, inductive coupling. And alternating current. So we use what's called three-phase alternating current. It's kind of an engineering thing, but if you rotate, it's like a few slides ago, I was showing a wire running past a stationary magnet, but you can have the other way too. You can have a magnetic field rotating past these inductors that can create voltages and create currents this way too. And the voltages will oscillate because we're talking about alternating current. But if you have three of them, then it kind of smooths it out. Okay. All right. Maxwell's equations. This is kind of graduate level stuff, but you know, I guess exposure. Boom. There you go. All right. And now I really just got two last things to tell you guys about, which are relativity and quantum mechanics. But the bell's going to ring here in about 10 seconds, so that's going to be a wrap on today. Yeah. So seniors, I'll miss you guys. Hope you guys do well in life. And everybody else, I will see you guys next week to tell you guys about relativity and quantum mechanics. All right, you guys have a great weekend.